Impossible for 1800. These 1800s factories defy modern technology, and historians can't explain why. In December 2025, a team of engineers and historians conducted an investigation of preserved 19th century manufacturing facilities in Lancashire, England, and what they discovered challenges conventional understanding of the technological capabilities of that era. Newly digitized documents from the British Industrial Archive, combined with forensic analysis of physical structures, reveal that certain textile and metalworking factories from the mid-1800s possessed engineering capabilities, manufacturing precision, and operational efficiency that in some respects rival or exceed modern facilities. We're not talking about nostalgic romanticism. We're talking about measurable facts, machining tolerances requiring precision tools that supposedly didn't exist, power transmission systems operating with efficiencies comparable to modern electrical systems, architectural structures using principles formalized decades later, and processes achieving consistency that modern engineers find difficult to replicate without automation. How is this possible? How did 19th century manufacturers, without electricity, without computers, without many of the fundamental tools for modern manufacturing, achieve results that defy expectations? The first tempting answer is that they didn't, that we're misinterpreting the evidence. Careful analysis reveals that records are consistent, artifacts exist and can be measured, and contemporary testimony corroborates extraordinary capabilities. A second explanation is that knowledge was lost, that artisans possessed expertise accumulated through generations that was discarded when we shifted to mass production. There is substantial truth in this explanation, but it doesn't tell the whole story. A third possibility is that we have an incomplete understanding of the history of industrial technology, that development was not linear but full of parallel paths, forgotten innovations, and capabilities that flourished briefly before being abandoned for economic and social reasons rather than technical limitations. Let's examine specific evidence from various facilities, explore what capabilities they demonstrated, how they achieved them, why knowledge was lost, and what we can learn. This is not just an academic question. Understanding how artisans achieved remarkable precision without modern tools has implications for sustainable manufacturing, production resilience, and engineering education. Impossible tolerances. Machining precision without modern machines. In November 2025, a metrology team from the University of Manchester examined preserved components of an 1867 coreless steam engine originally installed at Quarry Bank Mill. Using contemporary measuring equipment, including coordinate measuring machines with micron precision, they discovered something extraordinary. Machining tolerances on critical piston and cylinder surfaces were within 0.002 inches, approximately 50 microns. For context, this is the tolerance we would expect from a modern CNC lathe operating under computer control. How was this achieved in 1867 using a hand-operated lathe? The first reaction of many engineers is skepticism. Measurements must be incorrect, components must have been reworked later, or perhaps parts are not original. But extensive documentation exists. Records from the original manufacturer, the coreless steam engine, company, describe manufacturing procedures in detail. Components have original manufacturer marks and machining characteristics consistent with 19th century tools. And this is not an isolated case. Examination of multiple preserved Victorian-era steam engines consistently reveals surprisingly tight tolerances in critical components. How was this achieved? Through a combination of techniques that are fascinating in their sophistication. The first technique was scraping, the manual scraping of metal surfaces using a single-handed cutting tool. The craftsman would apply a thin die to a reference surface known to be accurate, then press the work surface against it. High points where metal made contact would receive dye. The craftsman would then meticulously scrape these high points, repeating the process hundreds or thousands of times until the entire surface made uniform contact. This process is incredibly laborious, but can achieve flatness within micron. Evidence of scraping is visible on historical components as a characteristic pattern of fine marks across the surface. The second technique was lapping, a process where surfaces are finely polished using progressively finer abrasives. Again, this is a manual process that requires skillful judgment on when to progress to finer abrasive, how to apply pressure evenly, and when the surface has reached the desired finish. Victorian-era apprentice training documents describe how an apprentice could spend months just learning to feel surfaces correctly. A third technique was the use of jigs and elaborate fixtures made with the same precision as the parts being manufactured. These tools allowed for repeatable and controlled positioning of workpieces, even with relatively simple machine tools. Manufacturers invested enormous effort in creating and maintaining these master tools. But beyond techniques, there was a culture of precision. 19th century engineers and craftsmen were obsessive about measurement and verification. Records show that critical components were measured multiple times during manufacturing using micrometers and other precision instruments that, although mechanical rather than electronic, were capable of remarkable resolution, and standards were rigorously maintained. The British Association for the Advancement of Science established dimensional standards in the 1860s that were disseminated throughout industry. The result was that different manufacturers working in different locations could produce components that were interchangeable, a concept we associate with modern manufacturing, but which was achieved through meticulousness rather than automation. If you're starting to realize that the history of industrial technology is more complex and surprising than simplified narratives suggest, leave a like now. Subscribe to the channel and activate the bell for more explorations of surprising historical technological capabilities. And if you want to support this work of bringing fascinating insights into the history of engineering, click the Hypar button below. Your support makes it possible for us to continue investigating these extraordinary stories. Now let's explore power transmission systems that rival modern efficiency. Mechanical power transmission. Efficiency without electricity. One of the most impressive capabilities of Victorian factories was the transmission of mechanical power through systems of shafts, pulleys, and belts. Modern analysis of EI. Preserved installation at Helmshorn Mills Museum revealed that the power transmission system operated with an overall efficiency of approximately 85%, comparable to modern electric drive systems when losses from converting electrical energy to mechanical energy are considered. The system consisted of a main water wheel 50 feet in diameter, rotating a horizontal main shaft that ran the length of the factory building 300. From this main shaft, power was distributed through vertical shafts to each floor and then through secondary horizontal shafts to individual machines. Each connection used a combination of perfectly cut bevel gears, lubricated bronze bearings, and precisely stretched leather belts. When we measure the energy available at the water wheel versus the energy usable in the final machines, the losses were surprisingly small. How was this achieved? First, through meticulous shaft geometry design. Victorian engineers had a deep understanding of torque mechanics, moments of inertia, and resonant frequencies. Shafts were dimensioned not only to withstand loads, but to operate at speeds that avoided resonant vibrations that would waste energy. Preserved engineering drawings show detailed calculations that are mathematically correct according to modern principles of machine dynamics. Second, through precise manufacturing and alignment of components. Bearings were hand-scraped to ensure perfect contact with shafts, minimizing friction. Gears were cut using dividing. Machines that allowed precise angular spacing of teeth. Belts were made of high-quality leather treated to maintain flexibility and strength. Third, through obsessive maintenance. Factory records show that resident engineers performed daily inspections, applied lubrication on regular schedules, and replaced components at the first sign of wear before they caused cascading problems. This level of attention ensured that the system operated continuously close to design efficiency. Fourth, through innovations in speed control. The problem with mechanical transmission is that everything operates at the same speed or fixed speed ratios, but different machines require different speeds. The Victorian solution was an elaborate system of stepped pulleys and moving belts that allowed for speed changes while the system was operating. An operator would pull a lever that moved a belt from one pulley to another of a different diameter, changing speed instantly. This required careful design to ensure that belts did not come off during transition. When we compare this system with modern electric drives, there are advantages and disadvantages. The obvious disadvantage is that the mechanical system requires a lot of physical infrastructure and space. The advantage is that once built, it is incredibly robust and can operate for decades with proper maintenance. There are no electronic components to fail, no vulnerability to voltage spikes or power outages. During a December 2025 investigation, engineers tested a system at Helmshorn Mills that had not operated in 40 years. After basic lubrication, the water wheel was engaged and the entire system came back to life, operating smoothly as if it had been used yesterday. This demonstrates an important principle. Well-designed mechanical systems can have exceptional longevity. Structural architecture, engineering principles. Before they were formalized, Victorian factories were not only mechanically impressive, but also architecturally. Structural analysis of Saltaire Mills, built in 1853, revealed the use of engineering principles that were supposedly not formalized until decades later. The main building is a multi-story structure with internal spans of up to 40 feet without intermediate supports, built using a combination of cast iron columns, wrought iron beams, and brick vaults. When modern structural engineers analyzed the design using finite element software, they discovered that the structure is remarkably optimized. Columns are positioned exactly where load analysis would indicate. Beam sections vary along length to match bending moments, and the vault system distributes loads efficiently. It's as if the architect had access to finite element analysis in 1853. How was this achieved? Evidence suggests that Victorian engineers used a combination of available mathematical theory, accumulated practical experience, and experimentation through scale models. The theory of beam bending was developed by Galileo and refined by mathematicians such as Euler in the 18th century. 19th century engineers were familiar with these theories and could apply them through laborious manual calculations. But beyond theory, there was a tradition of model building. Before constructing an expensive structure, an engineer would build a scale model, usually of plaster or wood, and test it by applying loads. Areas that failed in the model would be reinforced in the actual design. This iterative process of design through physical testing was surprisingly effective. Preserved documents from Sir William Fairbairn, a prominent Victorian-era engineer, describe extensive testing programs where beams of different configurations were loaded to failure. Behavior was measured, and results were empirical design rules. These rules were then published and shared throughout the. Another impressive aspect is the to-load distribution. Factories were designed to withstand not only static equipment loads, but also dynamic loads from operating machinery, which could create significant vibrations. Structures incorporated damping elements and were designed with generous safety factors. The result is that many of these buildings are still standing 170 years later, having survived not only aging, but also changes in use, removal of original equipment, and in some cases bombing during wartime. A November 2025 investigation at Dean Clough Mills in Halifax revealed an additional intriguing aspect: passive temperature control. The building was oriented to maximize natural light through large windows, but a ventilation system using roof monitors and internal ducts created natural airflow that moderated temperature even without mechanical systems. On hot summer days, hot air rose and was exhausted through roof monitors, while cool air was drawn in through lower vents. The system was surprisingly effective, keeping the interior significantly cooler than the outside temperature without any input energy beyond natural convection. Manufacturing process is consistency without automation. The most perplexing aspect may be product consistency. Analysis of preserved fabrics from the 1870s revealed that variation in yarn density, thread count per inch, and tension properties was within 2 to 3%, a level expected of modern manufacturing with automated control. How did human operators achieve such uniformity? The answer lies in a combination of machine standardization, intensive training, and elaborate quality control systems. First, textile machines had precise adjustments that, once set, remained constant. Mechanical looms had hundreds of adjustments, but once a skilled operator adjusted them, they produced consistent fabric. Manuals described adjustment procedures in meticulous detail. Second, operators underwent extensive apprenticeship, often beginning in childhood and progressing through years. A master weaver could hear the sound of the loom and know if something was wrong, detect invisible imperfections, and make adjustments that optimized quality. Tacit knowledge was key to consistency. Third, quality control was incorporated into the process. Supervisors constantly inspected output. Fabric that did not meet standards was rejected immediately. The piece rate payment system created an incentive because rejected fabric meant no payment. But there was a culture of artisanal pride. Producing quality work was a matter of professional identity. Fourth, there was standardization of input materials. Factories established relationships with suppliers and specified characteristics. Batches were tested before use. Metallurgy and materials treatment. Deep empirical knowledge. A December 2025 investigation of preserved tools from Sheffield, a center of steel toolmaking during the 19th century, revealed material properties that baffle modern metallurgists. Tool steel from 1880 has a combination of hardness, toughness, and wear resistance that is difficult to replicate, even with modern computer-controlled heat treatment processes. Metallographic analysis shows an extremely fine and uniform microstructure that indicates precise temperature control during quenching and tempering. How was this achieved? Without precise thermometers or electronically controlled furnaces? Through deep empirical knowledge, accumulated over generations, and meticulous observation of physical indicators. Sheffield blacksmiths developed extraordinarily sophisticated techniques for judging temperature based on the color of the heated workpiece. They differentiated between dozens of subtly different shades of red, orange, and yellow, each corresponding to a specific temperature range appropriate for different operations. This was not guesswork, but skill honed through years of practice. Training documents describe apprentices spending months learning to judge temperature by color before being allowed to work on actual tools. But beyond color judgment, there were elaborate techniques for controlling furnace atmosphere. Atmospheric composition during heating affects whether carbon is added to or removed from the steel surface. Blacksmiths carefully controlled this by feeding specific materials into the furnace: bone meal, charcoal, sawdust, each creating a different atmosphere. And they controlled the cooling rate during quenching by choosing the quenching medium. Water cools very quickly, oil more slowly, brine at different temperatures. A blacksmith would choose a medium based on steel composition and desired properties, sometimes even using staged quenching, where the piece was first cooled in one medium, then transferred to another. Records show that specific recipes were developed for different types of tools and were kept as trade secrets. Modern analysis of these historical processes reveals that, although blacksmiths lacked modern knowledge of transformation diagrams or crystalline structures, their empirical methods were precisely achieving microstructural transformations that a modern metallurgist would intentionally design. They arrived at the correct answers through a different route. Another impressive aspect is metal forging and shaping. Victorian-era forged parts have grain flow that follows the contours of the piece in ways that optimize strength, exactly as a modern engineer would design using software. This was achieved through forging techniques developed through experience, where the blacksmith understood how metal flowed under hammering and guided the work to create the desired structure. A December 2025 study compared Sheffield tool blades from the 1870s with modern equivalents of the same nominal steel composition. Performance tests showed that historical tools retained a sharp edge through more cutting cycle, had better impact resistance, and less tendency to chip. The difference lies in heat treatment and mechanical work, not in composition. This suggests that some practical knowledge was actually lost in the transition to automated processes. Measurement and control systems. Precision through mechanical instrumentation. A common misconception about the Victorian era is that a lack of electronics meant a lack of precision. Examination of instruments at London's Science Museum reveals how wrong this misconception is. Entirely mechanical 19th century instruments achieved resolutions that rival electronic instruments. Mechanical micrometers from the 1870s could resolve 0.0001 inches, approximately 2.5 microns. Chronometers were accurate to fractions of a second per day. Levels and theodolites allowed angular measurements to arc seconds. How was this achieved? Through ingenious mechanical design and meticulous manufacturing. A micrometer works by converting rotational motion into measured linear motion. Precision depends on the perfection of the screw thread. Victorian manufacturers produced screws with errors of only microns through iterative processes of cutting, measuring, and correction. Instruments were not only precise, but robust. Many function perfectly today after 150 years. In addition to measurement, Victorian factories had elaborate systems for process control. Centrifugal governors controlled motor speeds through pure mechanical feedback. Pressure gauges, temperature gauges using bimetallic expansion, and flow instruments provided continuous monitoring. Recorders created permanent records of parameters over time. Research in November 2025 at Manchester Museum examined recorders from the 1890s. Traces show remarkably stable control of pressure and speed over 12-hour shifts. Why knowledge was lost? Economies of scale and de-skilling. If Victorian capabilities were so impressive, why were techniques abandoned? The answer lies in the economic and social changes of the early 20th century. First, the development of power tools and automation. When electric motors became available, each machine could be powered independently. This allowed for more flexible factory layouts and eliminated complex transmission infrastructure. The advantage was clear enough that investment in conversion made sense, but knowledge about mechanical systems design became obsolete. Second, mass production. As markets grew, there was an advantage in producing large quantities of standardized products. This led to automated machines operated by less skilled workers. Instead of a master craftsman adjusting each piece, a machine operator fed blanks. This reduced costs but meant that artisan skills were no longer needed. Third, the change in workforce structure was a shift. The Victorian apprenticeship system, where young people spent years learning a trade, broke down due to social changes and labor laws. Formal education replaced workshop apprenticeship. This had advantages, but meant that tacit knowledge transmitted through direct practice was lost. The fourth factor was two world wars. Wartime production demands accelerated the move toward mass production. Labor was directed toward war, and factories needed to operate with inexperienced workers. After the wars, there was no going back to old methods. The fifth factor was the success of modern engineering. As theory became more sophisticated and computers became available, it seemed obvious that modern methods were superior. But in this transition, nuances were lost. Rediscovering lost knowledge. Modern industrial archaeology. In recent years, there has been growing interest in rediscovering historical manufacturing technique. Industrial archaeologists, historians, and engineers are collaborating to understand how artisans achieved their results. A project in December 2025 at the Iron Bridge Gorge Museum involved reconstructing an 1850s forge workshop using period equipment. After months of practice, participants began producing tools that approached historical quality. This demonstrated that techniques can be relearned but require dedication. Another project involved forensic analysis of historical structures. Laser scanning creates digital models that can be analyzed. Engineers try to understand design decisions, why a column was placed here, how the ventilation system worked. Insights are informing modern sustainable design. There is also interest in the conservation of operational historical facilities. Several preserved mills in England still operate original machinery using hydraulic power. These are not just museums, but functional production facilities. Operating them requires maintaining traditional skills and understanding original principles. In the academic field, historians are reassessing narratives of technological development. Instead of linear progress, they are documenting parallel paths, innovations that were explored and abandoned, and capabilities that existed briefly before being lost. Lessons for modern manufacturing, sustainability, and resilience. A study of Victorian methods offers valuable lessons for contemporary challenges. The first lesson is sustainability. Factories operated on renewable sources, water, wind, steam. Systems were designed for maximum efficiency because energy was expensive. Buildings used natural light and passive ventilation. Equipment was built to last for decades and be repairable. Contrast this with modern manufacturing, which assumes cheap energy and designs for replacement. The second lesson is resilience. Mechanical systems were robust to the failures that plague modern systems. There was no dependence on grid electricity, no vulnerable electronics, no software. Once operating, it could continue indefinitely with basic maintenance. There is something to be said for fundamentally robust systems. The third lesson is tacit knowledge. Modern manufacturing seeks to automate everything and make processes independent of individual operators. This has advantages but creates vulnerability. If automated systems fail, there is no one with the knowledge to diagnose them. The fourth lesson is designed for longevity. Victorian equipment was built with generous safety factors, high-quality materials, and a design that facilitated maintenance. 150-year-old machines still work. Contrast this with modern equipment designed for a specific lifespan and difficult to repair. The fifth lesson is diversity of approaches. The Victorian era saw multiple technical solutions being explored. Modern manufacturing converges on standardized solutions, creating fragility, practical applications, reviving techniques in modern contexts. There is growing interest in applying historical techniques in modern contexts where they offer advantages. In areas with limited access to reliable electricity, mechanical systems based on renewable sources may be appropriate. A project in rural India installed a water-powered mill using Victorian principles. After initial investment, operating costs are minimal and the system is maintained locally. In small scale, precision manufacturing. Some workshops are rediscovering that manual techniques produce superior results for certain tasks. Manual scraping of bearings, for example, can produce surfaces with better friction than modern methods. In the conservation of historic buildings, understanding original techniques is essential for proper repairs. In engineering education, some programs incorporate hands-on projects that require students to build devices using only hand tools. The goal is to develop an intuitive understanding of mechanical principles. And in the maker movement, There is interest in tools that do not require complex industrial infrastructure. The future of industrial archaeology and knowledge preservation. Preserving and understanding historical skills is becoming simultaneously more important and challenging. Important because the more complex our systems, the more vulnerable they are to failure. Maintaining knowledge of alternative approaches provides resilience. Challenging because the number of people with direct knowledge is decreasing. Documentation efforts are critical. Digitizing documents, 3D models of artifacts, recording artisans demonstrating techniques, preserve information. But documentation has limitations. Tacit knowledge embodied in bodily practice is difficult to capture. The only way to preserve it is through transmission via learning. Organizations dedicated to the preservation of crafts play a vital role. The Heritage Crafts Association identifies crafts at risk and connects artisans with apprentices. But sustainability requires that skills be economically viable. There is a role for public policy, subsidies for training, incentives for businesses that use traditional methods, support for industrial heritage sites. If this exploration of amazing Victorian manufacturing capabilities has changed your perspective on the history of technology, leave a like now. Subscribe to the channel for more fascinating investigations into how our ancestors achieved extraordinary feats. Click on the video appearing on the screen to continue discovering incredible stories of historical engineering. Thank you for joining us on this journey through manufacturing history. See you in the next video.